Now, unknown variance. Unknown variance is sigma is unknown. This is a simple. Instead of z, we will replace with the t value. That's it. Nothing different. How the logic to make a decision, conclusion is still the same. Only difference is instead of z value, we're gonna use a t value. So if you use a critical value method, we will calculate instead of z, we will calculate the t. And of course, we will use s, and so on. So problem here is that since we calculated using this value, my t may not be on the table. So you should find out using the Excel. Or you can, even though your t is not on the exact the table, but still you can compare this t is a more rare case or not. So let's look at the example. So hot chocolate. So this is about the temperature. Temperature should be 142 Fahrenheit. So random sample of 24 cup of hot chocolate is taken. And then this is 140, 140, 141, 145, and so on. So sample mean is 141 point, so x bar is 141.375, and the sample standard deviation is 1.99592. So you can calculate, put this number into the Excel, and then you can calculate by average. And the sample standard deviation is just use standard deviation. Then you can calculate this one. Now, confidence level is the 10%. Alpha is 10. Does this sample evidence show the true mean differ from the 142? So this is a slightly different, slightly smaller, but the question is it different? So our null hypothesis will be, our mu is same as 142, and the alternative hypothesis will be it's not the same, which means again this is a two-tail test. So which means the graph will be using like this, and then this will be the 90%, so which means this is 5, this is 5. Yeah, as I told you, this is our hypothesis. So this is the two-tail, and then since this is a t, not the z value, so you can look up the t value using the Excel function, and then degree of freedom is the 24 minus 1 is 23. So if you want to look at the Excel function, this is the Excel inverse. This 2t means it's a two-tail. So t value inverse means it's a probability 2t. Probability to the t, that's the inverse, is probability to the z, this is the inverse. This is the inverse. Because the z table, usually z is given, then you can get a probability, right? This is the normal case, but this is probability to the z with the inverse. Same, probability to the z. Here the 10% is the probability. And two-tail, that's why we don't divide it. That's just 10%, and degree of freedom is 23. Then you can calculate the t, which is a 1.714, which means In terms of t, this is a 1.714, this is minus 1.714. So if your t, you're calculating t is greater than this number or smaller than this number, then more rare case, then we're gonna reject. How can I calculate the hour t? You just plug in the number here. X bar is the 141.375 minus the mu 0 is 142. So again, we are assuming it's true. And then we want to check this is a more rare case or not. And if you calculate it, you will get a minus 1.5. Minus 1.5 is here, which means this is not the rare case. I mean, it's not rarer than the critical point, right? Which means maybe it's different, but our evidence is not strong enough. Still, we can have, by chance, we can have a 141.7375 Fahrenheit degree by sampling error. So we cannot say getting 141.375 cases is just rare enough. This is so can be happen. So still you can doubt the temperature is not 142, but our evidence is not strong enough. So we cannot reject. Again, this is not accepting our mean. The true mean is 142, but we cannot reject the null hypothesis, which is the mean is 142. We cannot reject null hypothesis. So you can use a p-value again. So once you calculate the t, and it's got a t, and then you can use a t distribution with a two-tail. Again, this is not inverse. So now your input is t, and the degree of freedom, the output will be the probability. So you plug in the t 1.534, and then degree of freedom is 23. Then you will get a p-value, two-tail. This is 0.2t is a two-tail. The p-value is a 0.13. This means it's about 13.87%, right? So our cut line was it 10%? Yeah, that's a 10% critical point. So this is greater than 10%. So the chance we can get a X bar 141.375 has a probability of 13.87%. So that probability is not rare than the 10% case, right? So probably this is just a sampling error. We don't know. Actually, we don't know this is really the smaller than the 142. However, the chance to getting 141.375 is a about 14%. So which is greater possibility than our cut line 10%. So we cannot reject. So take an action. It is doubtful whether the consumer could tell the difference in the hot chocolate temperature. So tiny difference means it's critical importance, even if it's statistically significant. So what it means is that even if actually our the result is statistically insignificant, but practically this is a lack of the practical importance. So even though it's a different, even though the true is this is 141 Fahrenheit, in practically the consumer can tell the difference or not? Of course, the practical importance is not important. So we should not take action. Yeah, our result is this is not statistically significant. However, even if it's statistically significant, so you should not do anything because practically it doesn't make any difference. So that's why the importance must be judged by the management, not by the statisticians. So confidence interval by the versus the hypothesis test. If this is a two-tailed test, directly you can use confidence interval because confidence interval has a both side. Two-tailed test has a both side. So if you calculate the confidence interval using X bar, and then the mu 0 is fall in between here, then you don't reject, and mu 0 is outside of here, the confidence interval, then you can reject. So if confidence interval does not contain mu 0, we rejected the null hypothesis. So you can try using our confidence interval here, and then as you can see, this will be the range is 140.677 and 100.2.073. So our mu 0, which is 142, is fall in between here. That's why we cannot reject. So confidence interval, you can use it if this is a two-tailed test. But you cannot use the confidence interval when this is a one-tailed test. Now, third case is about the proportion. So first case is about mean with a known standard deviation. Second one is the mean with the unknown standard deviation. Now, finally, is the test of a proportion. When we talk about the proportion, it's the same thing. Our z value will be this one. So same way is the p minus pi 0. This is usually the given number, just like a mu 0. And the standard deviation of the proportion. And again, the standard deviation of proportion is the pi 1 minus pi over n. So you just plug into this number, then you will get this formula. Yeah, let's take a look at the example. US airline mishandled 6 out of every 1,000 bag. Right? Find the 54% of this misleaded bag included was related to transferred. So 54% is related to transferring baggage. So they trying to use RFID to reduce this error, mishandling the proportion. And then the goal of decreasing the proportion mistake, right? So FlyFast would like to know if the wireless system has been effective. So after we use RFID, actually we reduce the the mishandling proportion or not. So this is only targeting the transfer. So can we reduce this 34%? The possible set of the statistical hypothesis could be the left tail, two tail, and the right tail, but which one will be the right one? Because since we are trying to reduce, you have to choose this one, right? So because they believe the RFID will reduce the proportion in my user left tail test. That's why. Return policy. Retailers such as H&M and Home Depot, Uniqlo, and Dick's Sporting Goods are employing new technology to crack down on return fraud. So return fraud means it's the customer who abuse their return and exchange policy. For example, some customer buy an outfit, wear it once or twice, and then return it. The retail equation, this is the kind of company, right? California-based company, license software that track the shopper's record of the bringing back item and alter the retailers when the customer's behavior is deemed risky. So just keep recording the who returned the item, how often, and then trying to find out the black customers, right? Goal is to reduce the number of fraudulent return, which should reduce the proportion of return of all. So if you prevent this return fraud, then the total proportion of return will be reduced in overall. So historical return rate of the merchandise is 13%. After implementing the software, there were the 22 returns in the sample of 250. So historical return was 13%, which is 0. This is a historical, and then now we got a 22 out of 250. At alpha is 0.05, which is 5%. This sample indicates the true return rate is below the historical return rate. So null hypothesis is it really small? So null hypothesis is not reduced, which means our P, the pi, is greater or the same as historical is 0.13, and alternative hypothesis will be the pi is smaller than 0.13, which means it's actually reduced. So we set the null hypothesis, and then we know alpha is 0.5, and then critical value of the z value. So you can find the critical z value because it's one tail. So you can just simply find out 5%. Then you will get a minus 1.645. And then you have to calculate your z value. Your z value will be, what is the 22 over 250? 22 over 250 is a 0.088. Right? This is a significantly small. So 0.088 minus the mean is what we assume is the 0.13 divided by, so here what proportion should I use is a 0.13 and 1 minus 0.13. Again, here what we are calculating z or probability is under the assumption null hypothesis is true. So we have to use this, and the sample size was 250. If you calculate it, right, this is the calculation. That's why I'm using 13% here, because this calculation is under the assumption our null hypothesis is true, and then we want to find out how rare my result is. So you can find out this is the minus 1.975. This is way smaller than minus 1.645. So this is a more rare case, right? This is critical, but this is critical point, but this is your z. This is critical, which means this is a more rare case. So we can reject null hypothesis, which means we can conclude the system actually reduce the proportion of return. This is a more rare case, then we can conclude. What kind of action we can do is we can use this system, adaptive use system in the other stores. So you can use a p-value. So in p-value, we are not looking for the critical, but this is the p-value, the z-value. And using this z-value, so this is minus 1.975, so let's use a minus 1.8, minus 1.98. Minus 1.9 and what was that? 8, right? So our probability, what it means is, what does it mean is our probability over here will be the 0.0239, which is about the 2.4%. So what is the probability that I can get a rarer case, more rare case than my number is just 2.4%. Since I will use alpha is 5%, this is a more rare case, so we can reject null hypothesis, which means number of return actually is smaller than 13%. So effect of the alpha, if you use the alpha, smaller alpha, which means this is a tighter. So how can I say, tighter critical. So getting more picky. To reject. So test statistics is same. Test statistics will not change by the alpha. This is the my number, and then the critical value will depends on the alpha. Critical value is different. So if you just reduce the more tighter, more picky, you can reject, but you cannot reject here. So as you decrease alpha, which means it's getting more picky, right? So you will have a smaller chance to have a type 1 error. So alpha does affect the decision. But you have to be careful. If you increase the alpha, the beta will increase. The type 2 error probability will increase. So what if we have all our assumption is the normality? So in the proportion, n times pi should be greater than 10 is the same rule, n times 1 minus pi should be greater than 10. Then our test will be the z-score, and we can assume the normality. But if it's not true, which means it's not true means it's badly skewed. Then you have to use the exact binomial test. You have to use a binomial distribution. And you have to calculate it again, same way, the p-value method is still valid. You can use. So what is the probability that we can get a more rare cases, and then that probability is smaller than your alpha, then you're gonna reject. However, how can I calculate the probability? You have to use a binomial distribution. And from now, this is optional, so I will just skip, but this is about how we can see the power curve. Power curve is, you can calculate the power, not only the null hypothesis, you have to assume what is the true means. So if the true mean is given, you can calculate the power, and then you want to have a high power, and then you can draw a kind of, you can calculate the probability of the sensitivity, which is the correctly rejecting the false null hypothesis, and so on. But I will just skip this part. And also the test for the variance. If we are trying to test the variance, so null hypothesis will be our variance is the same as a 94 or not, but I will skip this part. So you will not see the homework related to the variance null hypothesis, or you will not see any test exam problem about the hypothesis test on the variance or standard deviation. So I will skip this part. So if you are interested, and you can take a look. That's the end of chapter 9.